Hello everyone, welcome back. This is again C Programming, the introductory session of C Programming. So, the last time we talked about the enumerated type. That is a set of named values. Most of the time, the values are not significant, but items that are in the set itself add meaning to the type. So we also talked about the switch statement relating to enumerated type. And then an enumerated type doesn't provide everything we might need to model the real world. For instance, in a deck of cards, each card has both a suit and a face value, two different enumerations. Anyway, so we continue now with more complex data types, and here we'll cover the following topics. So, chapter 9, this is what we need to do now. This is about creating and using structures. Chapter 10, creating custom data types with type def. And then we continue with working with arrays. And then working with multi-dimensional arrays in chapter 12. And we continue to chapter 13, which is about using pointers. And the next topic would be understand arrays and pointers in chapter 14. And we continue with chapter 15, then working with strings, and we finish our section 2 with chapter 16, creating and using more complex structures. All right, now let's see what we have to talk about this time. So, creating and using structures, chapter 9. When a number of values all pertain to a single thing, we can keep them organized with structures. A structure is a user-defined type. There may be multiple values in a structure, and they may be of the same type or different types. A structure, then, is a collection of information representing a complex object. Well, with structures, not only can we represent complex objects more realistically, but we can also create functions that manipulate the structure in relevant ways. Just like data within a structure is grouped together in meaningful manner, we can also group functions that manipulate the structure together in meaningful ways. C is not object-oriented language. However, object-oriented programming has been primary focus of programming languages and programming since the early 1990s. It is extremely likely that after you learn C, you will be exposed to object-oriented programming concepts as well. Therefore, after we learn about C structures and the operations we can use on them, we will learn how C structures are logical transition to object-oriented programming. Now, thinking about the special manner then becomes a stepping stone to learn object-oriented programming. Okay, here we go with the topics: understanding how to declare a structure, understanding how to initialize the values of various structures. Then topic number 3, writing functions to perform simple operations on a structure. Number 4, modifying a structure to include another substructure. Number 5, understanding how C structures and functions are similar to and different from objects in other object-oriented programming languages. Let's get started. Let's go. Okay, now let's think about understanding structures. It would be extremely easy for C programmers if the world were simply made up of objects that were only numbers or names. Imagine if everyone were expressed as only a name or a series of numbers, but nothing else. In an automobile, so basically here you see vehicle identification number, so VIN, precisely describes various attributes of that car and uniquely identifies it. On the other hand, humans are far more complex than automobiles. Perhaps the world would be a very uninteresting place if we would use these things the same way for humans. For C programs to solve real-world problems, they have to be able to model real-world complex objects. C allows various aspects of real-world objects to be abstracted and modeled via three structures. So previously we talked about very basic objects, so two-dimensional shapes of the card, for example. Now why don't we do more? In fact, we haven't talked about it much as well. For playing cards, we need to be able to describe all 52 cards in the deck uniquely. To do this, we need both the card's sit and its face value. We might also need the card's relative value, and later we will learn how to put them in a collection so that we can represent the full deck of 52 cards. But for now, we will see how to accurately represent each card individually. And likewise, with two-dimensional shapes, we only represented a single basic aspect of them, the number of corners or sides that they have. Depending on the needs of the model, we may need to additionally consider the length of each side, the angles of each corner, and other aspects of the shape, such as its surface area. Now, if we were drawing a shape in a field, we would need to be concerned about its X and Y positions, line thickness, line color, field color, vertical ordering in relationship to other shapes, and possibly other aspects of the shape in the field. A shape structure might also need to contain other structures representing position and colors. A position would be a structure of the two values of X and Y coordinates, so representing the Cartesian coordinate system, right? A color would be a structure of four values representing red, green, blue, and transparency level. Now, we also talked about the conditional program flow. We considered calculation of for the leap year. The year is just one small part of a structure representing the date. Actually, some of the most complex structures are those that accurately represent date and time and then convert between all of the Earth's various calendars and time zones. Now, lastly, when we consider a structure consisting of multiple aspects, we must also consider the operations we can perform on that structure. This is similar to our basic data types and the operations we perform on those data types. However, because structures are custom to our specific program and problem domain, we must realize that we must also fashion the necessary operations on those structures, how to set and get information within them, how to compare one to another, and what other operations might be possible, such as adding a duration to time or blending two colors. Later, when we have collections of structures, we might want to order them, find a specific structure in a collection of structures, and perform other operations on them. But now let's declare structures. The structure type allows us to specify a group of related variables, each representing a facet or component of the thing being modeled. There may be just a few components in the modeled thing. More often than not, there are many components. Each component can be of any intrinsic C data type, for example, integer, real, Boolean, char, complex, and so on. So, as we learned in the previous chapters as well. The components in a structure do not have to be of the same type. Therein lies the power of the structure. It allows us to group various aspects of the thing into a single custom data type, in this case a C structure. We can use that data type much like we use any other data type. So the syntax for defining structures would look like this: struct name, type component name 1, type component name 2, and so forth and so forth. The type consists of two words, struct and name. The components of the structure are contained with the curved bracket 중괄호. Each named component in the structure is separated by a semicolon, and the definition of the structure is concluded also with a semicolon. Unlike intrinsic data types, components aren't initialized within a structure when it is defined. Initialization is done when a variable of that structure type is declared. So the definition of our enumerated type of card would be as follows. Here you see enumerated sit, club 1, diamond, heart, so on and so on, and then face 1, 2, 3, 4, 5, and ace, and then we have here sit and integer sit, and then face. You see here sit and face we put into enum, and then the remaining are done in a similar fashion. Notice that we must define the enumerations of enum sit and enum face before using them in our structure. Also note that enum sit and enum face, so custom types, are similarly named but still different from the sit and face variables. Remember that the uppercase letters uppercase letters are different from lowercase letters in identifiers variable names. We are adopting an arbitrary convention here that custom data types begin with an uppercase letter and variables of that type begin with a lowercase letter of the same name. Again, here custom data types begin with an uppercase letter and variables of that data type begin with a lowercase letter of the same name. That's why we have enum sit and a face. Okay, so our struct card now has enough information to accurately reflect playing card sits and face. We have added integer variables to hold the card's relative sit and face value. We might have chosen to use the values contained within enum sit and enum face, both, so sit and face here capitalized, but that might cause issues later on, so we have a separate component for each. In some card games, the ace is either high or low. In most card games, the sits have an ordered value, with spades being the highest and clubs being the lowest. For instance, in a card game, blackjack, sit value doesn't matter, and aces are the highest value card, whereas in some poker games, sit value does matter, and ace might be high or low. Anyway, our struct card is general enough that it can be used for each of these scenarios. Finally, we declare a card variable of struct card, again using the convention that the custom data type name has an uppercase name while an instance, so a variable of that type, has a lowercase name. The card variable is the overall name for a variable of 5 components, so sit, suit value, face value, and is wild. When the card variable is declared, enough space must be allocated to hold all the values of the components within it. If we assume that the enum types are 4 bytes and the boolean is 1 byte, then the result of size of card would be 17. So each time a variable of the struct card is type is declared, 17 bytes would be allocated for it. Note also that here we assume that enum types are the same size as int, so integer, and that a boolean is 1 byte long. The compiler actually determines the size of each enum type based on the range of the values it contains. Therefore, in reality, we cannot always rely on our assumptions. We can verify this, of course, within the following code we have here. Okay, let's add it into our card C. So the following, what we need is include stdio, right? And then include also std bool h. So let's continue with our enum sit here. And then club is 1, comma, diamond. Then we have heart, spade, and once we finished, then don't forget the semicolon, and then we go with enum face this time. You can put it there or there where you would like to have it. So anyway, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, jack, then queen, then king, and ace, and we finished our part. And we can move on to do the struck card. Let's see if we are so far already this time. Okay, we talked about it. First, let's do the int main part. It says so. Here we go, right? Int main void. So let's do that. int main void. Void is not necessary to type in, up to you. Anyway, so what are here? So struct card, struct card, and then the printf function. So printf enum swit is bytes so LU stands for long unsigned integer. Let's continue from here again. So size of and swit and I guess I can continue here with the next printf and face is and here face. Let's get done with the next printf as well. So int is size of int and then bool is lu okay lu bytes and size of bool. Done. Also the next one we need, if you remember, return 0. So we are done with this part 2. Okay, now let's move on and let's get back. So we have this printf now. Let's see what we have to talk about again. Okay, note that we use the type of the as the parameter of size of, and to print the result of size we need to specify the long unsigned integer in print function. This is what we have done. And then we could also use any declared variable as follows. So printf structured card, size of struct card, and card, because we create this struct card. And we should also create a struct card here. So struct card enum sit, then int sit value, then enum face, then int, so int face value, and bool is wild. And is wild actually should mean that it is not initialized until its first use. So that is wild meaning is about that. Okay, struct card, we have done it here. Well, we could take a look if that would work this time. And I have here some troubles. Let's see why we have it. Oh good lord, why do I do enum int and enum bool? I just realized what I have done. So now it should work. And yep, we got it. Good. Okay, now we can continue from here again. There is something I realized I did not put into. I did put here. It's the struct card I didn't use first, but then I added into my code. So you see here struct card. Double D, I don't understand yet why we have it at the moment, but yep, we should have it done. It's also good. All right, so we got everything and it works fine. Let's move on. Okay, so notice that we must define the enumerations of enum sit and enum face before using them in our structure. Also note that enum sit and enum face custom types are similarly named but still different from the sit and face variables. So lowercase right for variables, uppercase when declared as custom types. So remember that uppercase letters are different from lowercase letters in identifiers, so identifiers and variable names. We are adopting an arbitrary convention here. We talked about this one. Okay, so good. Then note that we use the type of as a parameter of size of to print the result of size. We got that part too, and actually we created our card C file and we saw the results as well. Now finally we calculated that struct card would be 17 bytes, but our task program shows that it is 20 bytes. What's going on? Let's see that again. So here you see again I and T. So we have actually 13, but we have 17 because of the D as well. Let's continue here with print f, and this time we go with struct card is and long unsigned integer, and we take size of Is it now good? Finally, yeah, finally. Okay, size of struct card and the next one is similar, but not this, but this, and size of card we can get now size of card. Similarly, just let's do this and return 0, and now we can see that what is stoked about. So struct card and I hope that I got exactly what I wanted. Actually, I got quite a different value here. I got here this time 32 bytes. Would be interesting to know why I got 32 bytes. Let me see the original code as well. So I'm taking my code out. And continue with the original code this time. And let's see what I did wrong. No, nothing. So got here 4441, and it said struct card is 32 byte. So I got 32 instead of 20 what the book actually says. Let's see the results and let's see the reasons, okay? What I mentioned before. So okay, first add another boolean value to struct card. Boolean variable to struct card. Do we have that completely done? Okay, let's see then this here, because I finished actually the entire code, that's why it says so. And let's also grab this part out. Actually, I could just well, let's do this. So, and let's now try it again. All right, so now we have it 444 and 1, so 4 4 4 4. I don't have here the face value, right? But I have the boolean. Let's add the boolean first. and then we have it as 20. Right now it's really 20. So basically that was my bad here. I already included everything. So if I just get rid of these values and I run it, then I should get exactly. So I got it right correctly. And then so this is correct. Okay. Looks better now, right? It's okay. But never mind. I still have it in this way. Okay, no problem. So not sure what I should do with this so that I get exactly what I want to have. Let's see if this time it would work. No. It's not what I wanted. So wait. 1, 2. 1, 2. I can't. I give it up. I give it up. I have only this, so done. I'm not doing the same way like the book, but yeah. Anyway, so what I wanted to show you is that if I add now Boolean, then I got this 20 bytes, and actually it's like how much is it again? So I'm set 4, integer 4, that is 8, and I'm face 4, that is 12. Integer again 4, so 16, and it should be 17, but we have here 20. And what's going on? So what's the reason? And that is what we see here. So that is why we talk about it here. It turns out that something else is going on behind the scenes. So that is called structure alignment. Where a given structure so where a given structure is padded with enough space, so given more space, that it contains an even multiple of the size of the largest component. Largest component is 4, so multiple 5 times that multiplication, right? And that's why we have 20. In the case of struct card, it is padded with 3 bytes, so that it will occupy an even multiple of 4, with 4 bytes being the largest size of any component in struct card. Now let's try 2 different tests. First, add another Boolean variable to struct card, which we have done. Notice that the structure takes the same number of 20. If I get one more Boolean, let's do that. Bool low. Okay, let's see that what it says. Still 20, right? Still 20. And run the program. So we got that. The 1 byte bool reduced the amount of padding needed, but the structure is still 20 byte long. Now add a double, a variable. That's why the double is added, right? So double variable to struct card and run the program, and notice that this time it's going to be 32 bytes. You see here, 32 bytes. Okay. Or an even multiple of 8, which is the size of a double. Double, it has the size of 8 bytes. That's why. Okay, if I add another integer, let's see, int, then it's gonna be 24. Remember, the size of the largest data type is given here. Okay, we got the double D, and the double D provides us a multiplication of 8. Padding within a structure can occur at the end or even in between components. Holes may appear between 2 consecutive components or after the last component. For the most part, we don't need to and shouldn't concern ourselves with how padding occurs within a structure. However, because of padding that's used to align structures, we cannot compare 2 structures as whole entities for comparison. If padding is present in the structure, the contents of that padding may be undefined depending on how it is initialized. Therefore, even if 2 structures have identical component values, the values in the padding are highly unlikely to be equal. Instead, if an equalated test is required, a function must be written to compare 2 structures component by component. We cannot do that right now. Initializing a structure and accessing its element. Now, once a structure is defined, we can declare variables of that type. The variables of that structure type must be initialized before use. C gives us a number of ways to do this depending on the needs of the situation. Given the definition of struct card, we can initialize a variable of that type in one of the 3 ways. First one, at time of declaration, the first way of initialization of a structure, the structure variable is at declaration time as follows. Here you go, here you see it. The structure component values are enclosed between the curved brackets separated by commas. The order is significant, and C1 is a card of the heart sit with suit value of the heart enumeration, and face of king with face value of the king enumeration, which is not a white card. In this form of initialization, we must be careful to get the order exactly correct within the definition of struct card. If we wanted a completely zero initial state, we could initialize all bytes in the structure with the following code. So struct card is 0. Entire structure is zeroed now. Zeroing the structure in this manner can only be done at the same time the variable is declared. After declaration, the entire structure in toto. In toto means actually nothing else but as whole, in all, overall. Okay, so all, overall. The second way of initializing to the corresponding component of card 2, care must be taken that these structures are of the same type, otherwise unpredictable results assignments may occur. This is because it is a bitwise assignment that assumes all of the components of each structure are identically positioned with padding with the structure type. And now number 3, after declaration component by component, lastly a structure variable or variable can be assigned explicitly component by component. When doing this, it is a good idea to first nullify or zero the entire structure at its definition. Each component is accessed using the dot notation, which specifies a given component of the structure. This initialization would look like the following. So struct card 3, and zeroed out, and then sit values, face value, and is y true or not. So here we go. And in this way, each component is accessed directly. The components do not have to be assigned in the same order that they are defined in the structure, but it is a good practice to do so. This type of initialization is done through component initialization. While tedious, it is often the most error-free approach since the structure can change. As long as the component names are the same, the code will not fail. When using this approach, it is also a good idea to initialize to some default state, which can either be all zeros or default value. You might need to create a default structure constant that is assigned to any structure variable of that type when declared as the following. So constant struct card default, and we have the default values then. Clearly, for our card example, having the default card doesn't make sense. In other scenarios, especially when the structure type is complex with many components, a default structure constant can provide highly consistent program behavior, since all structure variables will begin in a known state of either zeroed values or otherwise valid values. Let's continue with performing operations on structures functions. Except for assignment, there are no intrinsic operations for structures. To perform any operation on a single structure or within two structures, a function must be written to perform the desired operation. For example, earlier we mentioned a function that can be used to compare two structures for equality. This must be done by component, so as follows, you see here. Notice that we did not compare every component of the struct card in this function. We would only have to do that for absolute comparison, and when we need to compare each and every component for both structures. This just isn't necessary for our card example. Well, does it make sense to perform any or all mathematical operations on two structures? In general, no, not at all. But this answer is completely dependent on the nature of the structures you actually use. Now, for the card game, a blackjack, we need to add up the face values of our hand. First, we have to set up our face value with the proper values for blackjack. Then, we need to create an operation to add face value for two cards. We could do this in a couple of ways. The first way would be to simply add the face value of each card, accessing the component directly. as follows. So you see here, and I think this one we should do as well. Let me check out. Oh yeah, we have to have here a few things to do. Let's copy this first. And let's compare what we have here. STD boolean, boolean are good, spade good, 1 is good, so basically enumerations are all good. Struct card, enum sit, int sit value, enum face, int face value, no only one boolean and no double. Good. And bool is equal. Okay, that we have two function prototypes, as I see here, is equal struct card C1 struct card C2 int some cards struct card C1 struct card C2. Good. Then the mains are so far good, but we need also the struct. This we change to card 1, which is heart, integer heart, king, integer king, and false for boolean. Okay, the next one, struct card, card 2, card 1. So basically it says card 2 is now identical to card 1. Good. Struct card. Okay, we need to do struct card. Struct card 3. 0 it, as we have just talked about right now. Oops, this is done. Okay. And we need the following. We remember here the code we had just talked about. So card 3, sit, spade, and so on and so on. So let's do that. Card 3, sit, spade, and I copy paste this time all the others to keep them short this time so that I have everything done. Okay, let's see the next codes as well. What perhaps I forgot. No constant important here right now, but we have a boolean is equal. Here, this code I'm going to get out of my other code. So let's put that below the main. And return true, and we are done. So if C1 sit is not C2 sit, return false. If C1 face is not C2 face, and return false. If C1 is wide, isn't, then return false as well. So it's done. And then we have what else here to do? Let's see. Nothing more at the moment. So here, okay, the first way to do this would be to simply add the face value of each card. Here we go. We need to create an operation to add face value of 2 cards. So here, face value of 2 cards, accessing that component directly as follows. Hand value, it says, we do immediately this int some cards. So here we go. int some cards struct card C1 and struct card C2 and int face value C1 face value plus C2 again face value. It was easy. Luckily that C++ helped here. Return again face value, and we are done actually. Let's see if this code works now. And I save it as card 2 this time. Okay, we have some troubles here. Struct card undeclared. So let's see what is wrong. Okay, we are not yet finished, so that's the reason why we have this trouble. Let's continue first and then we can finish afterwards. Okay. Now that we can get the sum of 2 cards, integer card value, sum cards, right, we get it. Given these 2 approaches, one preferred over the other? Well, it really depends on a number of factors. First, we need to add the face value of cards in just 1 or possibly 2 places in our program. The former approach is acceptable. If, however, we must add face value in many places, it is better to consolidate that operation into a single function. Any changes or enhancements that must be made to the operation can then be made in a single place, the one function. All calls to that function would remain unchanged. Okay, so for example, what if aces could have either a high value, let's say 14, or a low value, let's say 1? If we use the former approach, we would have to be certain our ace face value was properly set before performing the addition. If the ace value could change or be either value depending on the situation, then we would have to add code to take that into consideration in every place that we added face values. In a latter approach, we would have to take the ace values into account in only one place, the add function. Notice that in the preceding function that the face value variable is different than both C1 face value and C2 face value. And also you might think that these variable names conflict because they have the same identifier name, but they don't. Face value is a local variable. The sum card function, so to the sum card function, and while C1 dot face value is a component of the C1 and C2 dot face value is a component to C2, each of them is actually a different location in memory capable of holding different values. Now let's put this concept into a simplified yet working program. This time it says copy the two programs and add the is equal and add the sum cards functions along with their function prototypes, and delete the body of main to replace with the following. So here we have it. Okay, let's do that. So we got it in main, struct card1, card2. We got it. Card3 we have here completely. Then this we don't need, I guess. Let's also check it. Yeah, we don't need it. Good. Instead, what we need is the following. So here we go. Bool cards equal is equal, and card1, card2, and printf this time card1 is %s equal to card2. I need to be able to type, I don't. And cards equal okay. So if not equal, then not, right? And done. And we need to add two spaces, and we are good. And let's go and take cards equal this time. Cards equal is equal card2 and card3, and this time card2 is equal to card3, and cards equal not, right? This is also good. And now printf the combined face value of card2 digits, right, is plus card3 digit is again a double basically. Okay, so we hold an integer here. And now we move on and do the following. So card2 face value. Actually, I wanted to add that one. Face value. Then next one, card3 face value. And some cards, card2, card3, and semicolon here, don't forget. Return, we got it, right. Now next one, boolean is equal, we have, right, and int integer we have, hopefully it works. No, it doesn't. We have here an int wrong. That would be this int, right? That's why we had it wrong. And we have it correctly this time. And we got the combined face value of card 2, so 13, and card 3, 14 is 27. We got it. We got it. We got it. So if you have the same results we finished here, now after initializing 3 cards with enumeration and integer values, we then use the function we wrote to compare 2 structures. For equality, we also use the sum cards function to add up the face value of 2 cards. Remember, here we have just done it, right? So here and here. And we assign this value to the face value, and we return that as face value. Okay, and note that while we can copy one structure to another with the equal operator, for any other types of comparison or operations on structures, we need to create and call our own functions. So far, we have created a structure that is composed of intrinsic types, so int, as well as custom types enumeration. We can also compose a structure out of other structures. And here I stop. We talk about structures of structures from here on, because I think it's enough right now for you, and let's stop here. Thank you very much for your attention, and see you the next time when we finish with this part. Bye bye.